Download this code from codegive.com, link in the description below. OK, let's dive deep into bug fixes and general code improvements, covering a range of techniques, tools, and strategies. We'll focus on writing robust, maintainable code and efficiently addressing issues when they arise. Understanding bugs and code quality. Before we start fixing bugs, let's solidify our understanding of what constitutes a bug and what qualities make code less prone to them. Definition of a bug. A bug is a defect or error in computer software or hardware that causes it to produce an incorrect or unexpected result, or to behave in unintended ways. Bugs can range from minor inconveniences, typos, layout glitches, to critical failures, crashes, security vulnerabilities. Sources of bugs. Logic errors. Flaws in the program's design or algorithm. Syntax errors. Mistakes in the code's grammar, example missing semicolons, incorrect variable names. Runtime errors. Errors that occur during program execution, example division by zero, accessing invalid memory. Concurrency errors. Issues arising from multiple threads or processes accessing shared resources without proper synchronization. Resource management errors. Problems related to memory leaks, file handle exhaustion, or other resource depletion. Data validation errors. Failing to validate input data, leading to unexpected results or security vulnerabilities. API integration errors. Issues related to incorrect use of external libraries, services, or APIs. Environmental factors. Bugs triggered by specific operating systems, hardware configurations, or network conditions. Code quality attributes. Readability. Code that is easy to understand and follow. Use meaningful variable names, consistent indentation, and comments where necessary. Maintainability. Code that is easy to modify and update without introducing new bugs. This often involves modularity and separation of concerns. Testability. Code that can be easily tested to verify its correctness. Well-defined interfaces and minimal dependencies aid testability. Robustness. Code that handles unexpected inputs or conditions gracefully. Error handling and validation are crucial. Efficiency. Code that uses resources, CPU, memory, network, effectively. Optimization should be balanced with readability and maintainability. Security. Code that is resistant to security vulnerabilities like injection attacks, cross-site scripting, and buffer overflows. 2. Preventing bugs, best practices. The best way to deal with bugs is to prevent them from happening in the first place. Here are some key practices. 1. Planning and design. Understand requirements. Clarify the exact requirements of the software. Ambiguity leads to misinterpretations and bugs. Create a design. Develop a clear design before writing code. This can be a formal design document, UML diagrams, or even just sketches on paper. Consider modularity and separation of concerns. Use design patterns. Leverage established design patterns to solve common problems in a well-structured and maintainable way. Example: singleton, factory, observer. 2. Coding practices. Write clean code. Follow coding style guides, example PEP 8 for Python, Google style guide for C++, Airbnb style guide for JavaScript. Use meaningful names. Choose descriptive variable, function, and class names. Keep functions short. Aim for functions that perform a single, well-defined task. Long functions are harder to understand and test. Asterisk avoid code duplication, dry, don't repeat yourself, extract common logic into reusable functions or classes. Asterisk use comments judiciously. Asterisk comments should explain the why more than the what. Good code should be self-documenting as much as possible. Asterisk prefer immutability. Asterisk immutable data structures can prevent many bugs related to unintended side effects. Asterisk use version control, git track changes to your code, collaborate effectively, and easily revert to previous versions if needed. 3. Error handling and validation. Asterisk validate input. Asterisk always validate input data to ensure it's within expected ranges and formats. Asterisk handle exceptions. Asterisk use try except, Python, try catch, Java, C++, or similar mechanisms to gracefully handle potential errors. Asterisk return error codes. Asterisk return appropriate error codes or status values to indicate success or failure. Asterisk log errors. Asterisk log error messages with sufficient detail to help diagnose problems. 4. Testing. Asterisk write unit tests. Asterisk test individual functions or classes in isolation. Asterisk write integration tests. Asterisk test how different components of the system work together. Asterisk write end-to-end tests. Asterisk test the entire system from the user's perspective. Asterisk use test-driven development, TDD. Write tests before writing the code. This helps you think about the design and requirements more clearly. Asterisk use code coverage tools. Asterisk measure how much of your code is covered by tests. Aim for high coverage, but don't treat it as the sole metric. Asterisk perform code reviews. Asterisk have other developers review your code to catch errors and suggest improvements. Asterisk use static analysis tools. Asterisk these tools can automatically detect potential bugs and code quality issues. Example Pylint, SonarQube, CodeWriting. Asterisk fuzzing. Asterisk feeding your software unexpected or random inputs to find crashes or vulnerabilities. 3. Bug fixing, the process. When a bug is reported, follow a systematic approach to identify, reproduce, and fix it. 1. Reproduce the bug. Asterisk gather information. Asterisk get as much information as possible about the bug, steps to reproduce it, error messages, screenshots, affected environment, etc. Asterisk reproduce locally. Asterisk try to reproduce the bug on your local development environment. This allows you to debug the code directly. Asterisk isolate the problem. Asterisk if the bug is complex, try to narrow down the area of code that's causing the problem. This can involve commenting out code, adding logging statements, or using a debugger. 2. Understand the code. Asterisk read the code. Asterisk carefully read the code in the area where the bug is occurring. Asterisk use a debugger. Asterisk step through the code line by line to see what's happening. Inspect variables, call stacks, and other relevant information. Asterisk use logging. Asterisk add logging statements to print out the values of variables or track the execution flow. 3. Identify the root cause. Asterisk formulate a hypothesis. Asterisk based on your understanding of the code and the bug's behavior, develop a hypothesis about the root cause. Asterisk test your hypothesis. Asterisk try to modify the code in a way that confirms or refutes your hypothesis. Asterisk refine your hypothesis. Asterisk if your initial hypothesis is incorrect, refine it based on your new findings. 4. Fix the bug. Asterisk write a solution. Asterisk modify the code to fix the bug. Asterisk test your solution. Asterisk write unit tests to verify that the bug is fixed and that no new bugs have been introduced. Asterisk consider side effects. Asterisk think about the potential side effects of your fix. Could it introduce new problems in other parts of the system? 5. Prevent regression. Asterisk Add a regression test. Create a new test case that specifically targets the bug you just fixed. This will help prevent the bug from reappearing in the future. Update documentation. If the bug revealed a gap in the documentation, update it to reflect the correct behavior. Share your knowledge. Communicate what you learned from fixing the bug with other developers. This can help them avoid similar mistakes in the future. 4. Code examples, Python. Let's illustrate these concepts with some practical Python examples. 1. Input validation *. Explanation *. This example demonstrates input validation. The function checks if the price and discount percentage are valid numbers and within acceptable ranges. If the input is invalid, it prints an error message and returns none. 2. Error handling with try except *. Explanation *. This example uses try except to handle potential errors like division by zero and incorrect data types. If an error occurs, an error message is printed, and none is returned. 3. Unit testing with unitest *. Explanation *. This example uses the unitest module to write unit tests for the add function. Each test case checks a different scenario, positive numbers, negative numbers, etc. To run this, save the code as a .py file, example test_add.py, and run it from the command line, python test_add.py. The output will indicate whether the tests passed or failed. 4. Logging *. Explanation *. This example uses the logging module to log messages at different levels of severity, debug, info, warning, error, critical. It demonstrates how to log information about the program's execution flow, errors that occur, and important events. The logger.exception method is particularly useful for logging exceptions along with their traceback information, which can be invaluable for debugging. To see the log output, run the script. The output will be printed to the console, or a file, depending on how you configure the logging. Static analysis tools. Static analysis tools automatically analyze your code without executing it, looking for potential bugs, code quality issues, and security vulnerabilities. They can catch errors early in the development process, before they become more difficult and costly to fix. Here are some popular options. *Pylint, Python, a widely used linter for Python. It checks for style errors, potential bugs, and code complexity. You can install it with pip install Pylint. SonarCube *, a comprehensive platform for continuous inspection of code quality. It supports multiple languages and integrates with many IDEs and CI/CD systems. ESLint, JavaScript, a popular linter for JavaScript. It helps enforce coding standards and detect potential errors. *Covrighty *, a commercial static analysis tool that detects a wide range of security vulnerabilities and code quality issues. 6. Debugging techniques. When a bug is difficult to reproduce or understand, you may need to use more advanced debugging techniques. Using a debugger Set breakpoints pause the execution of the code at specific lines to inspect the program's state. Step through code execute the code line by line to follow the execution flow. Inspect variables examine the values of variables to see how they change over time. Evaluate expressions evaluate expressions to check their values. Examine call stack see the sequence of function calls that led to the current point of execution. Remote debugging debug code running on a remote server or device. This is useful for debugging production issues or applications running in complex environments. Post-mortem debugging * analyze the state of the program after it has crashed. This can involve examining core dumps or logs to determine the cause of the crash. Divide and conquer *. If you have a large code base, try to narrow down the area of code that is causing the bug by commenting out sections of code or using conditional compilation. 7. Profiling. Profiling is the process of measuring the performance of your code. This can help you identify bottlenecks and optimize your code for speed and efficiency. CPU profiling * measures how much time is spent in each function. Memory profiling * tracks memory allocation and deal location to identify memory leaks or excessive memory usage. Line profiling * measures the execution time of each line of code. 8. Security considerations. Input validation * always validate input data to prevent injection attacks, buffer overflows, and other security vulnerabilities. Output encoding * encode output data to prevent cross-site scripting, XSS, attacks. Authentication and authorization * implements strong authentication and authorization mechanisms to protect sensitive data and resources. Use secure libraries * use libraries that are known to be secure and well maintained. Regular security audits * conduct regular security audits to identify potential vulnerabilities. 9. Regression testing. Regression testing is the process of retesting existing functionality after making changes to the code. This is important to ensure that the changes haven't introduced new bugs or broken existing functionality. Automated regression tests * create a suite of automated tests that can be run automatically after each code change. Manual regression tests * perform manual testing of critical functionality to ensure that it is still working as expected. Continuous integration and continuous delivery, CI/CD. CI/CD is a set of practices that automate the process of building, testing, and deploying software. This helps to reduce the risk of errors and improve the speed and reliability of software releases. Automated builds * automatically build the software whenever code is changed. Automated tests * run automated tests to verify the correctness of the code. Automated deployment * automatically deploy the software to production or staging environments. 11. Bug tracking systems. Use a bug tracking system, example Jira, Bugzilla, GitHub Issues, to manage and track bugs. This helps you prioritize bugs, assign them to developers, and track their progress. Good bug reports include clear and concise description * describe the problem clearly. Steps to reproduce * provide detailed steps to reproduce the bug. Expected versus actual result * explain what you expected to happen and what actually happened. Environment information * include information about the operating system, browser, and other relevant details. Severity * indicate the severity of the bug, example critical, major, minor. By incorporating these techniques and tools into your development workflow, you can significantly reduce the number of bugs in your code and improve its overall quality and maintainability. Remember that debugging is a skill that improves with practice. The more you debug, the better you will become at identifying and fixing bugs. Good luck.